Hello and welcome again to my physics online video lecture series. In today's video we're going to be talking about the LC oscillator circuit. We want to look at basically the equations that go with that, so essentially a loop rule and the results of that loop rule. Before we do, we should recall some of the materials that have been covered in previous videos. There are a few that we could reference. There's both the RC and RL circuits, and this right here basically just is the general approach, which is to set up the Kirchhoff loop rule, use it to get the differential equation that you'll then solve for, in the one case, charge on the capacitor as a function of time, and in the other case, the current in the resistor as a function of time, and from there get whatever other parameters you might want. In both sets of these circuits you could then solve for ultimately like current, voltage, energy stored, or power dissipation as functions of time, and in the case of the RC circuit also the charge stored. The other thing worth recalling is, since we've titled this LC oscillator, would be just simple harmonic oscillation. Simple harmonic oscillations are governed by an equation of the form, let's say that we're doing an oscillation in some parameter x, then it would be x double dot plus omega squared x is equal to 0, where x double dot just simply is a way of writing the second derivative with respect to time of whatever your parameter x is, so d squared x by dt squared. And so, for example, we had the spring where x is position, and the result was that x as a function of time is given to some amplitude or maximum displacement, which I'll call x max, times the cosine of omega t plus some initial phase angle. And in the case of the mass on a spring, this omega term is such that omega squared is the spring constant Ks divided by the mass m. So I think that's good for our review part of this video. Let's get on to the new stuff, which is the LC circuit, or the LC oscillator circuit. So imagine that you have a circuit that is as labeled here, and we initially have some amount of charge plus Q and minus Q stored on the two plates of the capacitor. And then we close this switch so that current is sort of free to move, charges are free to move about, etc. What is going to happen? Well, basically the charges that are on the capacitor will start moving through the inductor, and that in turn means that you're going to have a sudden current through the inductor, which is going to have an induced EMF, which means that there will be some voltage across the inductor as well that sort of resists this initial current and is proportional to di dt. Eventually the capacitor will be all done discharging, but at that point there will be a fairly large amount of current running through the inductor in the opposite direction, and then that current will sort of start dying down as it charges up the capacitor in the opposite direction. And so basically you get something like this little 4-frame animation cartoon that I've put together at the bottom, where you start off with a very low amount of current and a lot of charge on the capacitor. That current builds up to the point where it's at its maximum when the capacitor is discharged, but that means that more charges keep moving from top plate to bottom plate. Soon the charges are flipped, and then the whole situation starts over in reverse, and then it flips, and so on and so forth. So what is the equations that govern this? Well, as with the others, we should turn to the Kirchhoff rule. Basically, what we're going to do is apply the Kirchhoff voltage law to this situation, and we basically want to maybe look at it at the moment when the switch is closed. And the Kirchhoff voltage law basically says that delta VC plus delta VL is equal to 0. And then in using what the capacitor's voltage is, remember that the charge on the capacitor is Q equals V times C. So delta V is Q over C. And then for the inductor, you have the induced EMF is negative L times dI by dt. Now, recall that the current is the rate change of the charge. Thus, what you have here is Q over C minus L times d squared Q over dt squared is equal to 0. And now I can sort of rearrange this equation by dividing everything by a negative L. And what I end up with is d squared Q by dt squared sort of minus plugging in the voltage rule for plugging in the definition of the capacitance, which is C is defined as Q over delta V, means that delta V is Q over C, and plugging in the definition for the induced charge, and then taking care to keep track of polarity and signs within your voltage law, you end up getting this equation for your oscillator. So from here, what you have to do is recall that current is the rate change of charge dq dt, and thus that di dt is in fact d squared q by dt squared. So now you can sort of rearrange this equation a little bit by dividing everything by L and by sort of replacing this in to here. What you end up with is d squared q by dt squared plus 1 over LC times q is equal to 0. So this has the same form as our simple harmonic oscillation equation, where d squared x plus omega squared x is equal to 0. So if omega squared is equal to 1 over LC, then this looks like q double dot plus omega squared q is equal to 0. It follows that the solutions to charge as a function of time must be of the exact same form as the solution of displacement as a function of time was with the spring harmonic oscillator. Thus, the differential equations are shown here, and their solutions would be for q as a function of time is going to be whatever the maximum charge is. Basically in these diagrams it would just be plus or minus q, but I'm using q as a function of time now, so we'll use q max, times the cosine of omega t plus some initial phase, and in this case we would say where this omega is omega squared equals 1 over LC. Over here for the spring harmonic oscillator, what we end up getting is that x as a function of time is x max times cosine omega t plus phi naught, where again we can define our value for omega such that omega squared is the spring constant divided by the mass, so ks over m. So that is our equation for the oscillator, for the LC circuit oscillator. Basically what this does is it lets me figure out what the charge is as a function of time given the inductance, the maybe maximum charge, and the capacitance. Now note that just as with the spring, I could figure out what v of t is by doing dx by dt and getting essentially negative omega x max times the sine of omega t plus phi naught. Same is true down here. I could figure out what the current is by using dq by dt, and that in turn will give me negative q max times omega, or omega times q max, times cosine, times sine of omega t plus phi naught. And so now I have the current as a function of time. And I can do this to figure out other parameters, like maybe I want to know what the voltage drop across the capacitor is as a function of time. So divide this Q by C. Maybe I want to know what the inductor is, so I can either multiply this by negative L, or I can just use Kirchhoff's rule to realize that it should be negative of whatever I got for the capacitor. I can figure out what the energy stored is by looking at what the stored capacitance is and what the stored rate current is for the case of the inductor, etc. So that is the results of the loop rule. Alright, so let's close out this video with a quick example of an LC circuit then. You've been given a circuit. I've made a couple diagrams, sort of the initial state of the system, at which point the circuit is closed. We've been told that the inductor is 100 microhenries, so that is 10 to the negative 4 in henries. We don't know the capacitance. We do know that the initial voltage, delta VC, is given by 24 volts. And we do know that at time 10 nanoseconds, this voltage is 0. And so from that information, we want to figure out what the current is and what the value of the capacitance is. So how might we go about doing this? Well, we know that this equation of state that we've obtained is sinusoidal. So basically coming back to this equation, Q of t, and note that V of t across the capacitor must be Q of t divided by C. And so in other words, this would be Q max over C times cosine omega t plus phi naught. So we know that this voltage as a function of time should look like a cosine wave, and it's shifted left or right based on this initial phase. In the problem that we've been given, the initial phase is 0. So we expect it to look something like this. That means that this time right here represents one whole period, and this time right here represents 1/4 of a period. Note that the relationship between period and angular frequency is that angular frequency is 2 pi divided by period. So coming down here, we're basically being told that this is 1/4 of a period. Thus, we can determine that omega, which is 2 pi divided by t, must be 2 pi divided by 4 times 10 nanoseconds. Okay, so that ends up being 2 pi divided by 40 nanoseconds, or in other words, pi over 20 nanoseconds. So throwing that into account and recalling that a nanosecond is 10 to the minus 9 seconds, that this basically is 1.57079. So let's call it 1.571, just for rounding purposes, times 10 to the plus 8 radians per second. So we've just found omega. Now the reason why that's useful is because if you go back up to these equations, you'll notice that the implication of this pair of equations is that I is equal to I max, or negative I max as the case may be, when Q is equal to 0. So basically we're looking for, in the problem given, the maximum current. Okay, so we want I when Q equals 0, therefore I equals I max. And again, looking back at the equations that we have here, this term Q max times omega, this right here represents I max in much the same way as omega times X max is V max, the maximum speed. So we're basically just looking for Q max, or in other words, Q at this time times omega. So basically this is omega Q max. The problem is that Q max is equal to delta V max times C. So we actually need to figure out what the value of C is, the capacitance, in this circuit. So how do we find that? Therefore, what we're needing to do is solve for the capacitance before we can solve for this maximum charge. Now, to get the capacitance, which technically is like part B, what we can use is the fact that omega squared is 1 over LC, which in turn means that C should look like 1 over omega squared L. So what we're looking at is 1 divided by this number we found here, 1.571 times 10 to the 8 inverse seconds squared. So 0.571 times 10 to the 8 seconds squared times the inductance, which again was given as 10 to the minus 4 henries. So maybe call it 1.0 times 10 to the minus 4 henries. So that gives me a capacitance of about 4.0528 times 10 to the minus 13 farads. So if I'm rounding to two significant figures, this is about 4.1 times 10 to the negative 13 farads, or 0.41 picofarads of capacitance. So that's answer B. So now that I have that, I can get my maximum current, which I've labeled Q max here, but it's actually an I max. This is a Q max, Q max ends up being 24 volts times this 4.0528 times 10 to the minus 13 farads, and so multiply by 24, and you've got that the maximum charge must have been 9.7268 times 10 to the minus 12 coulombs. And now to get I max, you have to multiply this Q max by omega. So that gives me 9.7268 times 10 to the minus 12 coulombs multiplied by about 1.571 times 10 to the 8 inverse seconds. This is in inverse seconds. And so that gives me a maximum current, if I multiply that out, of about 1.528 times 10 to the minus 4. So let's call that about 1.5 times 10 to the minus 4 amps worth of current. So that's all for today's video. Hopefully you've learned something for it. As always, thanks for watching.